Hello and welcome back, everybody. Today in geometry, we'll be looking at that last section of chapter 7 for Jergensen and Moise chapter 14, which is, well, I guess equivalent in terms of section, which is 7. So this is what is known as the Power Theorem. And in other textbooks, there might be a name for it, or might be a different name for it, but this is the general name that you'll actually hear from most geometry. So anyhow, the Power Theorem is basically looking at secant and tangent lines and seeing how they are related to each other in terms of proportionality and also when they are put all inside the same circle. Okay, so here we have a total of 3 power theorem. The first one right here is this one where you have two chords, and it turns out that the chords, when they are going to intersect each other like this inside the circle, there is a relationship, and that relationship is actually right here, where A times B, meaning that you take the product of the two pieces of the chord, that is going to be equal to the product of the other 2 pieces of the chord that you actually have then. So A times B is equal to C times D. So here we're going to go ahead and do like a quick proof of that just to show you why that actually works out. The way we're going to do it is we're going to go ahead and form the following. We're going to go ahead and draw this line segment over here, and then we're going to go ahead and draw that line segment over here. Now, as you can see, we have 2 triangles as a result. So let me go ahead and draw those 2 triangles on the side so you can see how they are proportional, because most likely that's where we're going to get to. So the bottom triangle, you have the following. This angle right here should be congruent to this angle right here because of vertical angle theorem. Now, the other angles that are going to be congruent will be this one right here, should be congruent to this angle right here, because if you notice that where C is located and where B is located, those are where you have inscribed angles that are referring to the same arc. So because they have the same inscribed arc, they have the same arc on the outside, and that means their inscribed angles are going to be congruent to each other because they're both half of the measurement of the measurement of the arc. So because of that, then that means the 2 triangles are similar to each other. And now let's go ahead and pull out the sides that we have. So A is located right here, C is located right here, B is located right here, and D is located right here. Now, in terms of proportionality, we got to make sure we match side for side. So let's see here. I definitely do C corresponds to B because they're both going to be between the 2 angles that are congruent to each other. So therefore, A corresponds to D over here. So in terms of our similarity setup, then I'll go ahead and set up the following then. A over C is then equal to D. Oh, sorry, that's not a D. This is a D right here. D over B. And if you cross multiply, then you get A times B is equal to C times D, which is basically what we have right there. So that's your proof. Okay, now the second one right here, where you have, let's say the chords extend outward to an external point where they're going to intersect each other. And it turns out that in this case, you do actually have a proportionality as well that is written underneath right here. So I express them as A, B, C, and D. So then that means that the result is that A times B in this case is equal to C times D as well. All right, so just like the previous problem, what we're going to do is we're going to go ahead and pull out 2 triangles that are going to be similar to each other. Now, we also have to note that the 2 triangles are going to have to contain those sides that we have over here. So in addition, okay, well, technically there are a lot of triangles we can set up, but the best thing to remember this or think about like how to approach this is always look for maybe like some sort of inscribed angles that we can show that are going to be congruent. In this case, we do have some to work off of. First, I'm going to go ahead and create the chord over here. You can see that you have now kind of like an inscribed angle over here. And if I go over here and create another chord, you will then see another inscribed angle. And those 2 guys are definitely going to be congruent to each other. Now, the triangles that we're referring to, here, let me go ahead and draw them out then. So here's the first triangle over here where this length is supposed to be B. And then you have C, which is over here in this length. And then the other triangle that I'm pulling out is going to be kind of like underneath it, but overlapping at the same time. That is in reference, and this is D right here. And also, the other part is supposed to be A actually, which I need to kind of draw a little bit better. But hopefully you kind of get the idea as to like, where I'm getting this one right here. So here, let me just kind of rearrange this a little bit so we can see a little bit better. So it looks something like this right here, okay? So let me see. Okay, so here's D once again. Okay, so earlier we were saying that these two angles right here are congruent to each other because again they're referring to the same they're referring to the same arc. So that means that in here this angle is then congruent to this angle. And if you look at the angle over here between B and C, this one right here is the same as this angle right here because it's just a reflexive property. That is referencing to this angle over here. So then by again AA similarity, then that means that these two triangles are similar. Then that means now we can set up a proportionality. Just like in the previous problem, we're going to go ahead and match it term for term then. So let's see, B over here, the side that's between both angles is referring to or similar to or corresponds to D in this case. And then whereas C then, in this case, the angle that's the side that's next to the angle is going to correspond to A that's over here. So in terms of setting up what we have, then we can say B over C is equal to, for the other side, D over A. And if we cross multiply once again, we have A times B is equal to C times D. So there it is right there. All right, now for the last power theorem, here we have a kind of like a secant tangent scenario where again, they're going to meet at an external point on the outside. And once again, you're going to have a proportionality that we can set up in this case then. So the question is, where is that? So you can see all of this. So in this scenario, the proof is that I want to show that for the chord of the chord and also the secant that contains the chord, if you take the product of the let's see, the product between the secant and also the segment that's outside of the chord, those two right there are going to be equal to C squared, which is C is referring to the tangent then. So that means that C is basically like a geometric mean. So just like the other problems, we're going to have to find the two triangles that are going to be congruent to each other. You can probably get an idea that it's most likely this right here. That's going to be your first one. And then the other one is going to be over here, and that's going to be your second one. So let's go ahead and draw those triangles out on the side. So here's the first one, the big one up on top. So for the big one over here, we have C is this piece, and this piece is going to be A plus B right here. For the other triangle that we're looking at is going to be the one that's on the bottom, and hopefully that's going to be proportional to this one, where you see C over here and you see B over here. Now, just like before, we're going to go ahead and look at this part right here, which is the same as this, which is the same as this. So that means that by reflexive property, they are the same. Now, the next part is a little bit harder to see, but hopefully you can kind of make it out here. If you look at the inscribed angle over here, right? Sorry, not the inscribed angle. If you look at the arc that's over here, the inscribed angle is located over here, which if I call this x, then this over here is going to be x divided by 2. So that's going to be this guy over here. But at the same time, because of the secant tangent theorem, then that means that this piece right here must also be x over 2, and that is going to be this guy over here. So again, we have the AA proportionality, so therefore these two triangles are similar. And now we go ahead and set up the sides corresponding to whichever side it is. Let's first look at the side that is between the two angles that are given. So these two over here, so A plus B corresponds to C. And then afterwards, we have this side over here, C, corresponds to B that's over here. So writing everything up, let's see how that works out then. So we can have A plus B on the top triangle divided by C of the top triangle is equal to C, which is the bottom triangle, corresponds to B for the bottom triangle. Now if we cross multiply, then we should be able to get B multiplied by B plus A is equal to C squared, and there you go. All right, so now let's go ahead and maybe look at some problems that you can deal with these power theorems over here. So the first one, this is going to be algebraic then. So here is something where you have to solve for x. Okay, so let's go ahead and set up the power theorem. So in the first case, it's supposed to be x multiplied by x plus 17 is equal to 12 multiplied by 5. So hopefully that's not too bad. Now we're going to do some algebra. So x squared plus 17x is equal to 60. So x squared plus 17x minus 60 is equal to 0. So hopefully that we have something that we can factor. Look for two numbers that multiplies out to be negative 60 and adds up to be 17. So let's see. How about 12 and 5 in this case? So that should usually work out, right? So here is going to be 12. Here is going to be 5. And they're both going to be negative like this then. Let's see. Oh, no, positive. I'm sorry. It's going to be... No. Hold on. I think I messed up somewhere over here. Oh, it's not 12 and 5. My fault. It's actually 20 and 3. Okay, it's actually 20 and 3. Because negative 60, that's what we have. So 20 over here and negative 3 over here. So that means we now have x plus 20 as one factor and x minus 3 as the other factor. So x is equal to negative 20 and x is equal to 3. Now be very careful. X represents the length of a side because you can see x is located right here and also right here. So that tells me that x equals to negative 20 is what is known as an extraneous solution, meaning that even though we did solve for it, it's not an answer because it does not, it doesn't realistically apply to what we need then. Okay, next part. Here we have the secant tangent. So be careful about the secant tangent. The setup is that it's not 2 times 6 is equal to x squared. That's not the setup. It's supposed to be 2, which is the length of the outside segment from the secant, multiplied by the entire length of the secant, which is 2 plus 6. And all that is equal to x squared. So 2 multiplied by 8, which is equal to 16, is equal to x squared. So then that means that x is equal to plus or minus 4. But again, we're only taking x as positive because it's its length. Okay. All right. Now let's go ahead and take care of this last one right here, which is a proof. So let's see here how this works out. We're given that AB is a diameter. Okay. CD is a tangent. So you can see that over there at point B. I want to prove that AC times AG is equal to AD times AH. Okay, so let's go ahead and see where those sides are located. AC, that is going to be the entire length, okay? AG, that is going to be referring to this length over here, just a piece of it. And then we also have AD, which is the entire length over here. And then that's multiplied by AH, which is going to be this entire length over here. So we probably need to do something with those sides then. Okay, so here's what I'm noticing first. For this part, the diameter thing tells me that we're going to have AB, that's going to be a semicircle. And again, if we're referencing to arcs and we're looking at inscribed angle, what I would probably want to do is probably introduce some right angles, or actually some segments so you can see some right angles. So for example, over here we have BH, which we just introduced, and GB, which we just introduced. Now, according to what I just said, then that means that AHB should be a right angle, and then that means that this whole thing is going to be perpendicular, because remember that AB is supposed to be a diameter, so therefore the inscribed arc is supposed to be half of 180, which is 90 degrees. Over here, same thing. We're going to have AGB, which is going to be a right angle then. So let's see here. Now that we have that set up, let's see if we can kind of like, relate some of those triangles then. So I don't see a connection between those triangles, but maybe what we can do is we can focus on the triangles that those sides are located and maybe get something out of those. So here is what I'm looking at. Okay, so on the left-hand side, I have CBA, that triangle. Okay, we know that that's a right angle right there. And then we have G, which here, A over here, and B over here. Now, these two triangles, they definitely look like they are going to be similar to each other because we have two right angles right there. And also because they both share angle A. Now, what that means is there's going to be a similarity between those two. Now, from here, you can see that, let's see, AG, that is going to be calling for this side over here. So this is AG. Let me go ahead and color it with the red. Okay. And then we have AC, which is in reference to this side that's over here. Okay, so what I need to do is I need to make a proportionality with those two sides that are there then. Let's see. So that means that we're looking at this side right here, AB, that is going to correspond to AC to the side because both are opposite of the right angle. And then next to it, we also have AG, which is corresponding to this right here. So hey, look at that. So that tells me that AB is most likely going to be a geometric mean between the two. So let me go ahead and write that down then. So by AA, we can say that those two triangles are going to be similar to each other. Triangle ACB is going to be similar to triangle ABC. Okay, or sorry, not ABC. Let's see, ACB is going to be similar to triangle ABG. That was it. Okay, got it. And so as a result, then that means that we can have that as a geometric mean. So AB squared is equal to AG multiplied by AC. Okay, go over to the other triangle and do exactly the same thing. Okay, over here on the right hand side, I do believe if we do exactly the same thing, we can see that AB is also going to be a geometric mean, but to the other two corresponding side, because it looks like a mirror image, so you should be able to kind of like pull it out. But AG should be, AB squared should be equal to AH multiplied by AD. And since both AB squared are equal to the following, then that means that you can set this part right here equal to this part right there. So by transitivity, then we can say AG times AC is equal to AH multiplied by AD. And there you go. That's going to be our proof then. All right. Thank you so much for watching. I will see you guys next time then. Take care. Bye-bye.